All right, in this chapter, we want to look at our fundamentals of geometry. So we're just going to do a broad overview of a lot of the things that you would have seen in, say, a geometry class. So we start off on this first slide with just lots of definitions. So we've got the definition of a point, we've got the definition of a line, and we've got the definition of a plane. Then you want to think about, okay, now we're going to raise that into a different dimension. So by raising these things into a different dimension, that's kind of when we went from a two-dimensional into like a third dimension. So when we look at this, we want to take this idea of a point, line, and plane, and we want to look at it at 2D, and then we want to look at it at 3D. So one thing to notice is that I could put a point on a number line, kind of a one-dimensional space. Then I could put it on an XY axis in a two-dimensional space. And then we could put it on an XYZ axis in a third dimension type of a space. And so we look at this, when we look at our shapes here in just a minute, we'll look at things that are two-dimensional and three-dimensional. Okay. Another thing that we looked at in a geometry type class is our angles. Okay. So remembering everything's, when we talk about angles, is going to be based off of degrees of a circle, right? So when we talk about that vertex, it's just going to be that point of intersection from the center of the circle to any point on the outside of that circle. All right, so you can kind of see here we've got just a regular angle here. Then we put that angle into a circle. Okay, obviously all of these are not drawn to scale. So we see that when we start to talk about the degrees, we're talking about as the initial side turns to create what we call a terminal side. So here we've got an example of, say, 1 degree. Here we start with an initial side, and we're going to turn to a terminal side. We can see that angle is now formed. The vertex is that point in the middle of the circle. All right. And then the angle is there formed between our initial and our terminal side. Okay. Then we looked at types of angles. So there's some specific types of angles. Obviously you can measure any type of angle, but there's some specific types. So we have a right angle, meaning 90 degrees. We have a straight angle, 180. We have anything that's called acute, which an acute angle is just going to be anything that is less than 90. So between 0 degrees and 90 degrees. So it can't equal 0 and it can't equal 90, anywhere between. And on an obtuse angle, it's going to be anything greater than 90 degrees and less than 180 degrees. All right, so between 90 and 180. All right, so those were kind of our different types of angles that we had looked at. Again, this whole first slide is just basically looking at this vocabulary, reminding ourselves, because for some of us it's been quite a while. All right. Okay, carrying on with our kind of vocabulary here, we want to look at not only angles, but we want to look at lines, how that they could either intersect or not, that type of thing. So I could have perpendicular lines, they are specifically intersecting, forming 90 degrees, or we could have parallel lines that never intersect. I could just have regular intersecting lines where it's like the degree here, the angle does not matter, okay? But I do have two specific types, parallel and perpendicular, okay? So this was our intersecting, okay? Again, most of these terms, you know, when you look at them, you're like, oh, yeah, I remember that. But they're just on here just in case you need a quick reference, okay? Then as we move into a plane, so kind of an XY axis here, we start looking at these two-dimensional shapes. Okay, so one of these types of shapes would be a circle. All right, so remember the kind of key components to a circle. We've got a radius, we've got a center. You could think we also have a diameter. Radius is half the length of the diameter. Hopefully some of these things are ringing a bell here. Another 2D figure that we want to look at is a polygon. So a polygon, when we look at this, poly just means many. So we look at this to say, okay, well, a circle had no sides, right? Two sides can't make a shape. That's just that would just be a line. We have 3 sides, which we'll look at specifically here in just a minute. So a polygon technically starts when you have 3 sides, but that's got a more specific name. So really, polygon, we're looking at shapes that have 4 or more sides. Now, there are some specific polygons that you're probably familiar with, right? So we have a square or a rectangle. You've probably heard of maybe a parallelogram. You may have heard of a trapezoid. You may have heard of a kite. That kind of looks like a diamond if you're like, well, what's a kite? Okay, you've got your hexagon. You've got your pentagon. Oh, pentagon there. So there's lots of specific ones that you might be familiar with. Octagon, heptagon, so many and so on. However, we just want to kind of generalize them and say a polygon. So a polygon is any of those types of shapes. So you could see a lot of those different things. A regular polygon, for example, would be one that has all of the same angles and sides. Okay. So for our 4 sides, that would be a square. Okay. A rectangle is not a regular polygon. Even though it has the same angles, not all of the 4 sides are equal. So regular polygon means that they have all the sides and all the angles are equal. Okay, so there's a little bit more specific that we can get to, but in general, polygons, you're thinking of a lot of different shapes, anything 4-sided and up. Okay, then we have our triangles. We get a little specific when we talk about our triangles, right? So we have some triangles that are based off of our angles, some that are based off of sides. And so here we have we have an equilateral. Equilateral would be that all of the sides are equal. We could also have one that's called equiangular. Equiangular means that all the angles are equal. Okay, we could have something called an isosceles triangle. Isosceles means that 2 of the angles and 2 of the sides are congruent. More specifically, the 2 angles that are congruent are at the base of the 2 sides that are congruent. Okay. And then we have this idea of a right triangle. A right triangle means that I have exactly one angle that is 90 degrees. Okay. And typically they draw the little box in the corner there to represent a 90-degree triangle, or just really a 90-degree angle, right? Kind of, if you look back up to here when we're talking about those perpendicular up there, you saw the little box for the 90 degrees, okay? And then one that we don't know too much, you probably didn't look too much into this, but we have also an obtuse triangle. Okay, an obtuse triangle would be something where we have at least one angle that is an obtuse, or a angle where you have between 90 and 180. Okay, so we've got lots of different types of triangles. So now that we kind of explored and remembered a lot of things that we looked at probably in our middle school, high school career here about geometry, and some of you might use it on a daily basis, but now that we've reviewed some of those things, we really want to get into how is it going to apply mathematically to what we're doing. Okay, so what we want to really focus on is 2-dimensional and 3-dimensional shapes and being able to find measurements from those. Okay, so one of the measurements that we want to look at when we look at a 2D and a 3D shape is the perimeter. Remember, the perimeter is going to be the measurement around, or you can think about it on the rim of the figure. Okay, whether it's 2D, 3D, whatever the shape may be. Okay, and so typically when we're measuring perimeter, it's some sort of I'll see some sort of an addition happening there. So here's just some basic formulas when we look at 2D and 3D perimeters. Okay. So when we look at perimeter, remember we're measuring the space around. Okay. So in a two-dimensional type space, the word for that is perimeter. But when we get into a 3D type figure, a third dimension perimeter is really called the surface area. Okay, so some of us get confused because you're like, whoa, perimeter and area, those are two different things. Well, you're right, but in a three-dimensional space, the surface is really the rim. Okay, so the surface is what we want to measure around. Okay, so I'm going to add up here, the measurement around the rim, we can also think of the surface. So that might help us a little bit better. Okay, so the perimeter here and the surface area are the same type of measurements for a 2D and a 3D. All right, then when we talk about the area, okay, area is typically what's found on the inside of a shape. Okay, so I'm going to add us a definition over here that area is going to be the measurement of the interior, whereas the perimeter was the measure of the exterior. So when we think about an interior of a 2D, we would just call that regular area. But when we think of the interior of a 3D, we're going to think of the volume. Okay, so all of that's really the measurement of the area. Okay, so when we look at this, we want to think of this idea that the area and the volume go together when we go from 2D to 3D. Okay, so now that we've kind of got that terminology down, let's look at a couple examples and see if we can work through them. All right, so looking at this first example here, they've got a picture for us. That's pretty nice. So they've got this 4 foot by 6 foot rectangle, and they've got this semicircle on the top. So since we know that it's a rectangle, I'm just going to go ahead and measure the other pieces because we know that a rectangle has the same lengths on either side here. All right. Now, I'm just going to kind of look at this semicircle here. This semicircle is including that 4 foot across. So the 4 feet is actually going to represent the diameter of that semicircle. Okay, so remember it's a semicircle, semi meaning half, right? So it's half of a circle. When we want to look at the trim or being able to go around something, we're looking at the perimeter. So we want to find the perimeter of the rectangle. And so I'm going to add it to the semicircle. Okay, so the rectangle is going to be 2 length plus 2 width. And then I'm going to add that to the semicircle, which would have been 2 pi r or pi d. And I'm going to actually use the pi d this time. So let me erase that because we have the diameter. So it would have been pi times the diameter. However, it's a semicircle, so I'm going to put a 1/2 for that. All right. So now that we've got our formula, we're going to go through and plug in all of the things that we know about this. So I have 2 times my length plus 2 times my width. Then I'm going to add on to it 1/2 pi times 4. All right, I'm going to go type all that into the calculator. If you don't have a calculator with a pi button, you can always use that as 3.14. I'm going to type all of that in. I'm going to get 26.28. All right, this would be feet. Okay, so let's see if we can do our next problem here. It says you've built a stairway in a new house and want to cover the space beneath the stairs with plywood. What is the area? So either they straight up say the word area, or I look at this and I say, hey, this piece is filling in the interior of that triangle. Okay, so what I'm really trying to do is I'm going to try to find the area of a triangle. Okay, so it shows me here in my formula up top that the height is straight up and down. Now this is already a right triangle. So I've got my height to be 9 and my base to be 12. So the area formula is, area of a triangle, let me write it out for us, is going to be 1/2 base times height. So plugging into that, I would say 1/2 12 times 9. So I would get 54, and this would be feet squared. Okay, so area, we're going to square those units. All right. Hopefully we're kind of getting the hang of these. Let's look at the next one here. Oh, I went from an example 2 to 4. Sorry about that, a little typo. All right, so the next one, it says, one city block of the park is bounded by 2 sets of parallel streets. The street along the block, 55 yards along. The perpendicular distance between the streets is 39. How much sod should be purchased to cover the entire grass? So if I'm thinking about covering this, this is going to be, I'm going to cover something on the inside. That's going to be the area. All right, so I know I'm going to need area here. And this is going to be the area of what we call a parallelogram. All right, so I'm going to look at my formula. It says I want length times height, and it shows me here that the height is the total distance up to down. So it also told me that the perpendicular distance between the streets is 39. All right, so I can either use it from the picture. Let me erase that because I kind of drew all over it there. I can either look at it from the picture and find the measurements, or I can read it from my scenario up here. But I want to find my length, which is my 55, and my height, which is my 39. Okay, so my height, my length and my height. So I plug that in, 55 times my 39, and I would get 2,145. And since this is area, I would say that it's yards squared. All right, let's look at the next one here. It says a water reservoir has a rectangular base that measures 30 by 40 meters and vertical walls 15 meters high. So I'm just going to kind of draw this since they don't have a drawing for us. Now I'm no artist here, so Alright, so definitely not drawn to scale here, but we get the idea. So we've got our rectangular base here, which is 30 by 40. And then we've got a height going up here of 15. All right, so now it says at the end of the summer, the water depth was 4 meters. Okay, so first off, if I was filled to capacity, if I'm filling something inside, that means I'm looking at the volume. All right, so let's look at our volume formula. The volume of a rectangular based three-dimensional shape is going to be length times width times height. All right. Remember, I'm just getting that from the formula chart on the other page. So I'm going to plug in my 30 times my 40 times that 15, just so I can see what the full capacity is, so that when I am to take 4 meters out of it, then I would know how much I have. Okay, so my volume filled to capacity is 18,000. Okay, at the end of the summer, the water depth was 4 meters. So I only have 4 remaining. So I subtract some amount and I equal 4. So what that means, how much water was used, would be 17,996, right? Because if I were to add 4 to that, then I would be at that maximum capacity. And this is volume, so it's going to be meters cubed. All right. All right, looking at one more here, they've got a picture for us this time, and they ask me which can of soup is going to hold more. So I look at these 2 cans of soup here, and I say, well, they're the same measurements. Well, not exactly. So let's see what happens. So I'm just going to label this number 1 and number 2, and then we can go calculate if it's going to hold. That's talking about volume. So volume for number 1. And then I'm going to find the volume for number 2. And I'm going to see basically which one can hold more, which one has a greater volume. So I'm going to use my cylinder volume from the page before. So I'm going to use my pi r squared h. And they're both cylinders, so it's not too bad. All right. So on the first one, I'm going to have pi. My radius, well, if my diameter is 3, then my radius would be 1.5. And my height is 4. For my second one, if my diameter is 4, then my radius is 2. So I'd have pi times 2 squared. This time my height is 3. So let's calculate each of those and see which one actually has more volume. So plugging in my first one, I'll get 28.27, and I'm using the pi button, so if you aren't, you might get a little bit different. And then my next one, I'm getting 37 point, we'll round that to 7. All right, so now looking at these, even though the first one is taller, it actually will not contain more. The second one is going to contain more, because it's going to have 37.7 inches cubed for its volume. All right. So hopefully we kind of refreshed ourselves a little bit on how to find different measurements of 2-dimensional and 3-dimensional shapes. We can look at a composite figure, which is basically the first one we looked at where we had a rectangle and a semicircle. So I'm adding 2 things together. Maybe I'm looking at a 3-dimensional shape and I want the surface area. Maybe I want the volume. Maybe I'm looking at a 2-dimensional and I want the perimeter, right? So looking at that formula chart, being able to plug into all those different things. Okay. So the last thing that we want to look at here is this idea of a scaling law. So basically what that means, we looked at this a little bit when we were doing our conversions a while back, thinking about, well, if I wanted to convert feet cubed into yards cubed, right? So not only would I say, well, there's 3 feet in 1 yard, I would say there's 3 cubed feet in 1 cubed yard, right? So thinking about that, that's the same idea of this idea of a scaling law, okay? So the length, it's just the same exact scale factor. If I want to go feet to inches, boom, there it is. Okay, it's the same idea when I want to go from one perimeter to another perimeter, because perimeter is both the same units, meaning that if it's feet, there's no squared, there's no cubes to it. So any perimeter can relate to any other perimeter. Okay, if I want to go from an area, okay, so I'm looking at a perimeter now to an area, I would need to square my units, okay, because area is squared units. If I wanted to go from a perimeter up to a volume, I would need to cube all of the units. Okay, what I mean by that is if I know the sides and I want to increase it, okay, if I'm increasing it for a perimeter, I just add that amount on. If I'm increasing it for a area, for an area, then I want to square those units and add it on. If I'm increasing it for a volume, I want to cube those units and add it on. Okay, so lengths, keep it all the same. If I'm looking at area, I want to square it. If I'm looking at volume, I want to cube it. Just think of the units at the end when we were writing, okay, well, this is meters cubed. Maybe it was feet squared, right? Think about that exponent at the end, and that's what you're going to do to the units. Okay, so let's look at this final example, see if we kind of understand what's happening. So, suppose that magically your size suddenly doubled. That is, your height, your width, and your depth doubled. For example, if you were 5 feet tall before, you are now 10 feet tall. Okay, so it says, by what factor has your waist size increased? So we have to think about waist is a measurement of a perimeter, right? It's a measurement around. So if it is indeed a perimeter, then it's going to stay at the same factor. So if we are doubling, okay, then my waist will also double. Okay, my waist will also double. All right, now it says, how much more material will be required for your clothes? Well, think about your clothes. They are covering the area of your body. So when we think about our clothes, that's a measurement of an area. So our clothes are going to be double but squared. And it kind of sounds weird, but you think about if I'm doubling something, I'm really multiplying it by a factor of 2. Okay, so doubling is basically times 2. So area doubling square would be, my clothes would be multiplied by a factor of 4, right? Because area means I'm going to take what's happening and do it twice. So doubling a double is going to be quadrupling. Okay, so we could say a factor of 4, or if you want to use the words quadruple. Okay, then it says, so by what factor has your weight changed? So you think about weight. Weight is what's inside. It's our volume. Okay, so if we're thinking about weight, we're thinking about a volume. All right, so a volume is going to take that doubling and it's going to cube it. So it's going to be a double cubed. So remember, think about it as being times 2. So 2 cubed is going to be multiplied by a factor of 8, since 2 cubed equals 8. All right, so you want to think about perimeter. I kept that times 2. Area, I took that times 2 squared, which gave me my times 4. And then volume, I took that times 2 cubed, which gave me times 8. So that's how we're going to scale the different factors. Without knowing what the numbers are, we can scale it to be what we want.